Hello dear followers, and welcome to my first video tutorial from the MechTechPlace.net, my blog. I'm Alberto Lavatelli, a mechanical engineer, aerospace engineer, and we're here to talk about the circuit I designed to drive load cells and everything about how to run this circuit and specifically how to calibrate this circuit in order to get a correct sensing of forces or weight or however whatever you want. First, let me make a brief introduction of strain gauges load cells, since I know that for mechanical engineers or however expert in applied science is something really common, but I know that for many others, like makers or people who just want to play with physical computing, it is hard to understand sometimes how those cells work and why those cells need a dedicated circuit to be interfaced with microcontrollers or computers, DAQs. So let me first show you a load cells, how a load cell is before being instrumented. This is a load cell I designed for a control purpose, for specific tasks. Those cells, as you see, are mechanical systems which are subjected to forces, to specific kind of forces. For instance, this is a flexural load cell. This works with bendings. In fact, in this region, the load cell is clamped and forces are applied in this way. In fact, forces, any kind of load applied to these systems generate stress, and with particular shapes using holes and other artifacts, you can get stress concentration in some area. For instance, for this load cell, this area is subjected to stress concentration, and as a consequence, here is developed a sensible level of strain. So forces applied to structures develop stresses, and stresses develop strains. And the second thing to do is to sense strain using these particular kind of sensors, which are called extensimeters or strain gauges for US speakers. However, strain gauges are designed to sense strains in a particular way. When they're in normal conditions, they have a fixed value of resistance. When strain is applied, in fact, the fact is that in all load cells, extensimeters are glued in those zones where you have stress concentration. So in fact, they change their resistance due to strains. However, in metals, strains are really small. When they get big, metals get broken. You go to material yield, and so the problem is that if you try to use this sensor, the extensimeters, like you will use a common potentiometer, then you will get really small signals, and so it will be hard to sense forces. So what happens? In load cells, strain gauges are applied several times, and they are wired in the shape of a Whetstone bridge. I don't want to spend too much time talking about what a Whetstone bridge is and how it is run. However, feel free to email me if you have a curiosity about this topic. What you have to know is that these sensors need to be powered up by a really precise power supply, and then they need to be conditioned and amplified to hearable level. I mean, for instance, what is important is that you need a circuit that is able to transfer this little amount of resistance change to a signal which is much more amplified. So you can use load cells with common circuits, for instance, like Arduino or USB DAQs. So what is important is to use something to interface Whetstone bridge with the common word of analog inputs. So normally people can go to electronic suppliers like DigiKey or RS Components, and you can go there and buy those enclosures that are able to power up and amplify your load cells. However, this load cell amplifier most of the time cost more than $200, and so for instance, for hobbyists or for prototyping, it is not always is good to spend this money, and not always you have benefits from spending this money. So what to do? What have I do most of the time is to exploit these ICs, which stand for integrated circuits. They are specifically designed to sense Whetstone bridge sensors, strain gauges, pressure sensor, many of them. Um, those integrated circuits need to be wired in a particular way, like you see designed in my blog, and in this way you can interface load cells. Now, the main components of my circuits are really are really easy. These ICs, sorry, the INA125P. Then we have potentiometers, which enables us to set the gain, the amplifying gain of the integrated circuit. And then we have capacitors, which, to tell the truth, aren't really necessary. You can wire this circuit, my circuit, without using the capacitor. But the capacitors are good because they are able to filter the noise coming from the power supply, so you get a smoother signal. So now let me show you first in the how to wire the thing. Not To tell the truth, I will not show you how to wire my circuit on the breadboard, because I believe that you are able to follow a wiring diagram. But I will show you how to connect load cells and how to connect my circuit to a DAQ, and secondly, how to calibrate the circuit with the common linear calibration procedure, and how to get the proper conversion between a voltage output and weight applied, or forces applied, as you wish. Okay, now let's start with the experimental setup. Here we have a load cell, which is a Flexural one, 30 kilograms of load cell, sorry, and it is clamped to the desk. And here I made a simple loading unit. You can do everything you want here, but the most important thing is to be sure that bending is only generated by forces applied in this way, so you don't have concentrated moment bendings caused by the load not applied exactly in the loading direction. Okay. With this, using this tool, we will connect semi-calibrated weights. I like to say semi-calibrated because they are not perfect for the perfect calibrated weight, we will suppose that this will weigh 10 kilograms. But if you want to do a perfect calibration, you have to put it on a scale and then recover the exact mass of these weights. However, my first aim is to explain you how to calibrate those cells, not to how to make perfect calibration, because then it's only a matter of having really good calibration weights. Then the load cell is connected to the circuit I designed. Now, this is exactly the same circuit. You find it on the internet, but I decided to make a PCB board for my experimental activity, since I needed this circuit too many times, and also in printed circuit boards you get a really low level of noise. However, here you see the INA 125P. Here you see the potentiometer that sets the gain, and here you see the capacitor which filters the noise. Then we have the connectors, which are common screw connector, and here we can see the strain gauge wiring interface. Here you have the strain gauge power supply. Here you have the strain gauge ground. Then you have the two terminals of the Whetstone bridge. Well, what is important is for you is that when you connect your load cell, you follow up the diagram shown by load cell supplier. For instance, if you buy FeedJet's load cell, you can have it on the internet. Or in this case, this is a load cell made custom made, and here you have the wiring diagram. Okay, I know this is Italian, but okay, you can find it also in English. And so be really precise in doing this task, and not to connect the wrong wire. And so just use the reference wiring scheme that I put on the internet, and you can find on the MechTechplace.net. Then we have the circuit interface with DAQs. So we have here the 5-volt power supply. Here we have the ground, and on pin number 3 we have the circuit output. Now let me show you how I connect it to the National Instrument DAQ. Here you see the analog input, and then we have the voltage reference. Okay, in order to acquire the signal, I've made a dedicated software with LabVIEW Signal Express. Here you can see the DAQ MX acquire, which enables me to acquire the voltage coming from my circuit. Then we have a filter in order to reduce the level of noise, and then we have an amplitude and level calculator. This enables me to output this gauge. I made this because using DC level, you get rid of noise when measuring your load cell output. Now, if I run the circuit, you can see the voltage output of the load cell, and if I apply the load in the positive way, you can see the circuit outputting a bigger level of voltage level. Sorry. If I unload the circuit, it will return back to the 0 voltage level, And then if I load it on the opposite direction, the voltage level will go down. Then unloading, it will come up to the original level. If you see the plot, then you can see the forces going up and down as my hand swings up and down with forces applied here and here, as you can see, going faster and faster, and then I unload everything. So as you've seen, the load cell connected to my circuit is able to sense forces in the two directions, the positive and the negative. In fact, the main reason why I started to put my circuit on the internet is that if you go on the internet and try to interface Arduino with load cell, you can find 1,000 of solutions which are really bad in the sense that they're able only to sense forces in one direction, and the wiring is really poor. In fact, you cannot set up the gain in a really neat and clean way. While with my circuit you can sense forces in the two direction, and the gain you set leads you to a really repeatable measurements. So if you power up this circuit another time, you will get the same calibration. While for many circuits, as I saw on the Arduino forums, I saw that those circuits are not really repeatable. In fact, the calibration slightly changes every time, and also the calibration procedure shown in these tutorials I saw on the internet are really bad, really poor, and to tell the truth, not correct at all. So let's see how to calibrate load cells with my circuit. Okay, first thing you have to do is to set the gain to a level that you may like for your application. For instance, I want with this 10 kilograms applied here for the load cell to have an output more than 3.5 voltage. And so what to do? First thing, you have to put the weight, to apply the weight to the load cell. So here you see. Okay, now the load cell is loaded, and the voltage applied is 3.8. For instance, if I want a bigger amplification, I will turn the potentiometer in a counterclockwise direction, and then you see the output going up to 4.264 voltage, which is too much for my application. So I turn it counterclockwise and a little bit more. And then you see the thing coming back to 3.730. Okay, now let's see that everything is okay. By unapplying the load, as you see, voltage is going to the original point at zero load. Loading it again, it rises up to the desired level. So everything is okay by now. Okay, now that gain is set, what is really vital and what you have really to do is not to touch the gain potentiometer another time, because as soon as you touch and you alter the value of the potentiometer, you will change the calibration. So calibration is related to a specific value of resistance from the potentiometer. If you change the potentiometer, calibration has to be run again. Otherwise, the relationship between force is applied and the output of my circuit is not again true, is not again valid. So what you have to do is to lock the level. Okay, now that the gain is set, we have to choose a proper calibration path. So we have to choose what is the sequence of weight to be applied to our system. Now you can see that I already applied the 10 kilograms weight and got an output of 3.733 volts out of my circuit. Now what we have to do is to follow the loading path and apply 5 kilograms, 2 kilograms, 1 kilograms. Then we can register really by now the zero load level by running the circuit, and we see that it is 2.435. It is stable, and this is our zero level. Okay, now we finish the first run, I can say the positive run of our load cell. What now we're doing is to flip the load cell, turn it upside down, so if we apply the load in the same direction, it's like giving to the load cell a negative force value. So we can check that everything okay, and also by doing this we are really sure that the calibration will be good also for the negative forces. Otherwise it's not good to calibrate negative forces with only positive load. Okay, now you can see that the loading path is complete and we record a consistent set of data for our calibration. Here you can see a graph of the calibration procedure, and you can see that by now it is smooth and really similar to a line, which is good. Okay, now that we have all the parameters, we can use the built-in function of MXL, which is called linear regression. No, let me first you have to pick two nearby cells, otherwise the function won't work. So it's reg line in Italian. I don't know how it is in English, but first we have to select the output. Then we have to select the input. And then remember not to press only enter, because you have two cells to output. For double cell output or multiple cell output, you have to press Ctrl Alt Enter. Okay, these are the parameters. So we see that the zero load output estimated is 2.419, and the sensitivity of our load cell is 0.13095 voltage per kilogram. This is the end of the calibration procedure. If we want to add something more, for instance, if you would like to use this calibration with the Arduino board, we can estimate the conversion between bits and the load applied. In fact, we have n bits, which for Arduino, for instance, is 10 bit, equal to 2 elevated the number of bits levels, and so we can get the since Arduino is 0.5, we can get the sensitivity of Arduino, which is equal to 5 / the number of levels, and so we can compare. This is the sensitivity of Arduino, which is voltage over bits. And since we like to have the conversion kilogram bits, the only thing we have to do is to multiply a kilogram bits to multiply the inverse of the sensitivity of the load cell, which is kilogram voltage by the sensitivity of Arduino, which is voltage bits. And so we can get 0.03272 kilogram per bits. And this is the end of the calibration procedure. Please remember to do everything as said in the previous part. So remember to set a consistent path of load, like this one, and use the linear regression to estimate the correct zero load output and the correct sensitivity. This is a really error-resistant procedure because it comes from statistics, and then you can use this output to work with any kind of microcontroller or DAQ you want. So, in the end, we were able, with my circuit, to sense forces in 2 directions, and with this calibration you can run your experiments or your physical computing application the way you like. See you for the next tutorial.